Hello everyone, I'm Typhon, and in this lecture we will take our first steps into the exciting world of software-defined radio by building a basic amplitude modulated receiver, AM receiver. Think of it like an AM car radio capable of receiving AM signals and converting them into audio you can listen to. However, instead of working with the live radio signals right away, we will simplify things by using pre-recorded file of captured radio data. This approach lets us focus on learning without needing any hardware just yet. You can download this file from the resources section of this lecture. And at this stage in your STR journey, there are two key areas to focus on. The first is learning how to use GNU Radio Companion, a powerful tool for STR development. And the second is understanding the theory behind how STR works. In this lecture, we will concentrate on the first, getting hands-on with GNU Radio Companion, while we will touch on the radio theory later. The main goal here is to build your practical skills. So if some of the steps feel a bit like following instructions for assembling a model airplane, don't worry, this approach is intentional. As we progress through the few sections, we will revisit this AM receiver project to explore the underlying concepts in greater depth. By the end, you will not only know how to build a receiver, but also why each component works the way it does. For now, let's dive in. We will open a GNU Radio Companion and let's start building your first project. Let's start by creating a new flow graph. You can do this by navigating to File, New, Key to Graphical User Interface, the first one, and that's it. Or you can simply press Ctrl N. This action will open a basic flow graph template with two blocks already present in the workspace. Every new flow graph begins with these two blocks. The option blocks, this blocks contains the fundamental settings and some documentation for your flow graph. And this variable block, this represents a variable named samprate. So if you have worked with programming languages like C or Python, you can think of these blocks as a way to define and manage variables within the flow graph. Specifically, this samprate relates to the sample rate for your project. So think of this as a variable in programming language. While it is not strictly required, it is considered good practice to personalize the option block with some basic information. Now we will change the title. Let's change the title to like my first, or let's AM receiver project, or like AM receiver, and we will update the description. Let's say lecture on AM receiver. Next, we will add a new block to our flow graph. Specifically, we will enter the Q2 graphical user interface entry. We'll drag and drop here, which we will use this shortly. So to locate the new blocks efficiently, you can always press Ctrl F and type the name into the search box. So your flow graph should now look like this here. Let's organize this so it looks nice. Now let's take a closer look at this Q2 graphical user interface entry, a block similar to this variable block. This entry block stores a value that can be used throughout the flow graph. However, there's an important difference. The value in this GUI entry can be modified in real time while the flow graph is running. Now, it is a common practice to group variable blocks and entry blocks together at the top of the flow graph. While this makes your workspace more organized and easier to understand, it is not strictly necessary. So the flow graph will run the same way regardless of where the blocks are placed. To configure this entry block, we'll open it with double clicking on the to open its properties window, and we will change the ID field to frag, and we will set the default value to 880E3, which I will explain this right now. So now let's break this down. The notation 880E3 here is exponential notation, which stands for, let's open a notepad, which stands for 88,000, 880,000. So, or for this, times 10, 3 on the like small side, like this, right? So, the part after this E represents the number of zeros added to the number before it. For example, this here we wrote means is equals to this. Similarly, this equals to exponential notations is widely used because it makes large numbers much easier to read and interpret compared to their expanded form. Also remember this notation, it will come up frequently as you work with GNU Radio Companion. But here's the catch. If you click the apply, you will notice an error message at the bottom of the window. This happens because the default value you've entered isn't valid yet. The error message looks something like this, right? Now let's address this problem. Let's address the problem causing the error. This issue is related to data types. So far, we have learned that how flow graphs can be imagined as numbers flowing from sources through processing blocks and into sinks. However, we haven't yet explored what kinds of numbers those are. In GNU Radio Companion, just like a programming language such as Python, Java, or C++, there are different data types. Each data type determines what kind of numbers a block can work with. Now, take a look at the type property of this entry, QT graphical user interface entry block on your screen. By the default, the type is set to integer, meaning the block can handle whole numbers like both positive to negative, like 65. Oops. Yeah, like 65, 700, like 100,000, right? 100,000. Or like positive, negative numbers like 60 minus 65, like 500 or 5,000, like this. Now, this is where the usually arises. So the default value we entered earlier, this uses exponential notation, which creates a floating point value. The floating point numbers include decimal points and look like this. For example, p, right? Or minus 8.9. Since an integer type block doesn't accept floating point numbers, the mismatch triggers an error. And now we'll open this pull down menu in this type properties, and we will change the setting from integer to float, and then click apply. This adjustments ensures that the blocks can accept the floating point value we have provided, and the error will disappear. And here you will notice that the appearance of the block in the workspace has updated to reflect the value you've entered. This feature is incredibly helpful as it allows you to quickly understand the configuration of your flow graph at a glance, even as it becomes more complex over time. Now let's add another Q2 GUI entry block with a different ID and the default value. Instead of creating it from scratch, we can save time by copying and pasting the existing block. The newly created block will appear in this workspace with this ID set to frag_0 by default. So we will double click on the block to open its properties. We will change the ID to center frag, and we will change the default value to 900A3 and click apply. Because this block was copied, the type here is already set to float, so there's no need to adjust that setting again. Once you are done, your flow graph should look like this. While this isn't required, it is a helpful practice to keep all variable and entry blocks grouped together at the top of the flow graph. This organization makes your workspace easier to navigate as your project grows in complexity. Hello everyone, my name is Typhon, and now let's bring some radio data into our flow graph by adding a source block. Now to start, we will locate and add a file source to our workspace. This block allows you to use a file as the radio data input for your flow graph, which means you won't need an SDR hardware to proceed. This file here contains raw radio data captured from a real airwaves by an SDR enthusiast and saved for later use. If you were building a fully functional radio receiver, you would use a different source block designed to connect with your SDR hardware. That block will provide a real-time radio data directly from the airwaves. Next, we will configure the file source block. Double-click on the block to open its properties. In the File field, click the three dots and navigate to the project files you've downloaded earlier from the resources section of this course. I will also share it on my website. And we have selected the file named 2024 AM example typhonix.iq file. You might notice a warning at the bottom of the properties window saying the port isn't connected. Don't worry about this for now. We will address it shortly. At this stage, your property window should look similar to this. Once everything is set, we will click on OK to close the window and return to the workspace. And this is a good point to save your work. Press Ctrl S or go to File, Save. So you can use any valid Linux file name, but let's actually call it, let's say, first AM example or first AM receiver. That's it here. Now, when working on flow graphs, remember to save early and save often. This ensures you don't lose progress if something unexpected happens. From this point on, I will assume we are familiar with the basic steps for adding blocks, accessing their properties, and configuring their values. So instead of spelling out every action, we will focus on explaining what each block does and how it fits into flow graph. Let's move ahead and continue building. Now that we have set the file source, let's move on adding to blocks that will process the radio signal. Don't worry too much about understanding every detail just yet. We will delve into how these blocks works in later sections. For now, the goal is to assemble the functioning flow graph. Now we will start by adding a signal source to your workspace. This block generates a continuously repeating sequence of values that represent a sinusoidal waveform. Now double click on the signal source block to open its properties window. Now for the frequency property, instead of entering fixed number, type center frag minus, oops, also we need to change this to center frag. Now here signal source center frag minus free frequency here and here. Now you can see, let's open again, what just happened here. Instead of putting input a static value, you enter the mathematical expression involving variables, the center frag and frag. In fact, GNU Radio Companion allows you to use almost any valid Python expression for block properties. This feature is incredibly powerful and will make your flow graphs much more flexible. In this case, the frequency of the signal source is determined dynamically by subtracting the value of the block with the ID frag from the value of the block with ID center frag. After clicking OK, you will return to workspace. Notice something interesting. The block no longer displays the mathematical expression you entered, which this needs to be 900. I forgot to save the work. Now, here, the block no longer displays the mathematical expressions you entered, right, like this. Instead, it shows the calculated result based on the current values of center frag and frag. And again, in the workspace, you'll notice that the signal source block's frequency is displayed as 20 key or 20,000. This value comes from the calculation of center frag subtract by frag. With the default values we set earlier, center frag is 900,000 and frag is 880,000. So the result of this subtraction gives us 20,000, which is exactly what we are looking for. Next, it is time to add multiply block to the flow graph. This block will combine the outputs of our two sources. It is important to be careful here and ensure that you select the correct multiply block, as there are several blocks with similar names in the GNU Radio Companion library. Now, to connect the blocks, as you can see here, we need to get multiply here. So to connect the blocks, simply click the output port of the first block, such as one of sources, and then click the input port of the multiply block. You can also click in reverse order. The connection will work either way. When connecting the inputs to the multiply block, pay attention to labels next to the input ports. You will see in 0 and in 1 labels. These are the ports where you will connect your sources. In general, the inputs are on the left and outputs are on the right. But be aware that some blocks may be rotated. Once the connections are made, your flow graph should look like this. As you continue adding and connecting blocks, it is a good practice to take a moment to tidy up the flow graph layout. This helps with readability, especially as the flow graph gets more complex. You can click and drag blocks to reposition them. And notice that the connections between blocks are sticky, so they will follow along as you move move the blocks. So while organizing the flow graph isn't strictly necessary, to be honest, it makes them much easier to follow and understand. Now, let's proceed by adding low pass filter block. Now, this type of filter is essential in many the radio signal processing workflows because it removes or reduces unwanted frequencies. Filters like this will be explored in more detail in like section 6. But for now, configure the low pass filter block by setting the cutoff frag to 5E3, which is 5000, and transition width to 1E3, which is 1000, leaving all other properties as defaults. Now, once this is set up, connect the input of the low pass filter to the output of the multiply block. After doing so, your workflow should look like this. So by following these steps, you will have successfully proceeded the signal with multiplier and filter, which is fundamental technique for many signal processing tasks in SDR applications. At this stage, you may notice that the low-pass filter block's label appears in red. This happens because GNU Radio Companion actively checks your flow graph for errors as you build it. When a block has an illegal condition, its label turns red, indicating there's an issue. In this case, the problem is that the output of the low-pass filter isn't connected to anything. It is important to pay attention to these visual cues as they help you catch issues before running the flow graph. Other common causes for red labels include missing or invalid properties or connecting multiple outputs to a single input. Now, let's add AM demode block. This block will perform the critical function of demodulating the incoming radio signal, effectively extracting the audio signal that we can listen to. You can configure the AM demode block by setting its channel rate to the value of samp rate and it is audio decimation to 1. After configuring the block, you will need to connect its input to the output of the low pass filter block. When connected, your workload should appear like this. The AMD mode block will now responsible for translating the raw radio signal into something audible, allowing us to extract the audio content from the AM broadcast. So we will delve into specific of how the AMD mode block operates in next sections, but for now it is essential to recognize its role in the overall system. As you continue building the flow graph, there's an important detail you should be aware of when connecting blocks. The input and output ports of each block are color-coded. For instance, the AMD mode block's input port is blue, like the rest of them, while output port is orange. These colors are meaningful. They indicate that the type of data flowing through the ports. So blue ports handle complex numbers, while orange ports handle floating point numbers. At this point, we are not diving into the complexities of complex numbers, but it is important to remember this rule. Connections can only be made between ports of the same color. So if you try to connect an orange port to a blue one, the flow graph will signal an error, typically turning the connection to red. Keep this in mind as you progress. Now that we have addressed the color coding issue, let's move on to adding the rational resampler. This block plays a crucial role in adjusting the sample rate of the audio signal, ensuring it matches the requirements of your sound card. So we will set its interpolation to 32 and its decimation to 400. Once you've configured the block, connect its input to the output of AMD demode block, initially you may notice a red arrow appear between these two blocks, indicating that something is wrong, obviously. So the issue stems from trying to connect ports of different colors, orange and blue. Just as we mentioned earlier, this is similar to trying to pass an integer where a string is expected in programming. To fix this, we will open the rational resample blocks properties and change the type from complex to float to float, real tabs. After doing so, click OK, and the ports of the rational resampler block will now turn orange, and the red arrow indicating the invalid connection will change to black arrow as normal, confirming that the connection is valid. At this stage, we are very close to completing the flow graph. We have set up the sources, applied several processing blocks, and resolved the issue with the port color mismatch. However, we still need to consider one last thing. What are we going to do with the processed data? Right now, all the data flows through the blocks, but we need a sync to output the final result. So we will learn that in next lecture. To output the data from your flow graph, you will need to add an audio sync block to your workspace. This block is responsible for playing the audio through your computer's sound card, allowing you to hear the broadcasted sounds. Now here's how to set it up. We will place the block into our workspace. I will set the sample rate. We'll double click the audio sync block, and in the properties window, we will set the sample rate to 32,000, which is 32 kilohertz. Now, most computer radio hardware supports the 32 kilohertz rate. However, if needed, you can tweak the flow graph to select a different sample rate. Now, we will connect the output of the rational sampler block to the input of the audio sync block, like this. By setting this up, the audio from your flow graph will be output through your speakers, allowing you to hear the demodulated signal in real time. Now, let's address one last detail. We will adjust the sample rate for the flow graph. So you may have noticed that most blocks in the flow graph have a sample rate property to 32 key or 32,000. This value corresponds to this samp rate variable, which was defined at the beginning of the project. You can modify this variable to affect the sample rate for all blocks that depend on it. Double-click on the variable block with ID samp rate, and we will change its value to 400 kilohertz, 400 E3. And that's it. After making this change, you will notice that the sample rate updates through your flow graph, impacting the sample rate for all blocks, except this final block. This is a great example of how adjusting a single variable can propagate changes through the entire flow graph design. Now it is time to run the flow graph. To do so, we will simply click the play button, and once executed, you will begin to see some text scroll by the console. After a few seconds, you should hear some music. It might come with a bit of static, as is typical with AM radios, but you should clearly hear voices and music. The audio will loop after a few seconds because the file source block is set to repeat and it doesn't contain much data. So if you don't hear anything, double check your computer speakers to ensure they are properly adjusted. Let's stop this. So if you notice choppy audio, and if you're running GNU Radio Companion in a virtual machine, you may need to tweak the audio sync properties. So open the audio sync properties window and change the device name to sys default. So if you're not using a virtual machine, however, changing the setting isn't recommended. So earlier in this project, we discussed how you can modify the key to graphical user interface entry values while the radio is running. However, if you want to change an ordinary variable block like a sample rate, you will need to stop the flow graph, adjust the value, and the restart the flow graph to apply the changes. Now let's experiment with tuning to different radio station in the execution window. Hmm. Okay, we had the problem here. Let's change. Okay, now let's again here. So here we will change the value, the frag here to 750 kilohertz. 1, 2, 3. And after a brief moment, you will hear a different repeating chunk of audio. That's because you tuned into a new radio station. So you can also experiment with other stations by setting the frequency to, for example, 710 or 750 again, as well as a few weaker ones like this. In this section, you have successfully built a simple AM radio receiver using GNU Radio Companion. So before we dive deeper into the mechanics, let's take a moment to peel back the layers of your radio design and look at the big picture. At a high level, your AM radio receiver flow graph accomplishes the five main things. It injects pre-recorded radio data into the flow graph, it tunes to a specific AM radio channel by filtering out the other channels. It demodulates the signal of the desired channel. It performs resampling on the signal to match the audio playback requirements, and it plays the resulting audio through your computer speakers. As you go through this project, you may have a few lingering questions. For instance, how does a filter work? What does it mean to resample? And how does multiplying a radio signal by sinusoid help in tuning? Like with this, remember? So these are crucial questions that you will explore in the upcoming sections. By answering them, not only will you gain a deeper understanding of how your AM radio flow graph works, but you will also uncover some critical radio concepts that will prove valuable as you continue your journey into the world of software-defined radio. My name is Typhon, and I'm waiting you in next section.